Module 10, Lecture A, Customization.
By the end of this lecture, you will be able to implement custom keras layers by subclassing tf.keras.layers.Layer with build and call methods. Define custom loss and metric functions or classes compatible with keras training workflows, and integrate custom components into models and verify they save and load correctly. Building custom layers. Subclassing keras layers. Subclassing a layer in keras is useful when you need your model to capture ideas that are specific to your problem. It lets you define custom transformations, such as specialized normalization or attention mechanisms, while still working smoothly with standard layers. By expressing these operations as layers, you keep your model structured and modular, which makes complex architectures easier to build and understand. Subclassing also bundles the forward computation and internal parameters together, so the layer behaves consistently during training, evaluation, and inference. Subclassing in deep learning means creating a custom layer with its own clear lifecycle, much like a physical sensor. You specify how the layer is initialized, how it creates and manages its weights, and how it processes inputs during the forward pass. By separating setup from computation, this approach makes models easier to understand. Each layer has a specific role and predictable behavior, which helps keep the overall design organized and transparent. Subclassing a layer in deep learning lets you precisely control how it behaves inside the framework when standard layers are not enough. It allows you to add conditional logic, handle multiple inputs and outputs, and maintain internal state while still working with automatic differentiation and model saving. This is useful in applications like recommendation systems that adapt to user context, or scientific models that must enforce specific output constraints. By embedding these custom rules directly into the layer's computation, you keep your model both flexible and compatible with existing components. Python code subclassing keras layers. This script demonstrates how to create a simple custom layer by subclassing the TensorFlow keras layer base class. It highlights the basic structure and behavior of a custom layer without going into complex details. As you run it, you can observe how the input and output shapes change and how the layer behaves during execution. The goal is to give a clear, minimal example of custom layer implementation. The line starting with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version helps ensure the code runs with the expected features and behavior, since different TensorFlow versions can work differently. This command is usually executed in a terminal or notebook before running the rest of the script, so that the required library is properly set up. We begin by importing TensorFlow, the main library we use to build and train machine learning models. This import gives us access to its deep learning tools, such as components for creating neural network layers, compiling models, and handling data. With TensorFlow available in our script, we can define custom layers and train models using its full set of features. In TensorFlow, we set the random seed to a fixed value, such as 7, so that any operations involving randomness always produce the same results each time the code runs. This makes the model's behavior consistent across runs. As a result, experiments can be reliably reproduced during development and testing. This line displays the version of TensorFlow currently in use. It provides a quick way to verify which version of the library is running. Knowing the exact version is important to ensure your code is compatible with the library. It also helps when using specific features or tracking down bugs that may depend on the TensorFlow version. In keras, you can create a custom layer by subclassing the base layer class which lets you define a new type of layer with its own behavior. By doing this, you can override how the layer is initialized, how it builds its internal components, and how it processes input data. This approach is useful when you need special transformations or operations that standard Keras layers do not provide, while still allowing the custom layer to integrate smoothly into a Keras model. The custom layers initialization method first calls the parent class's initializer with any extra settings, so the base class is correctly configured. It then saves the initial scale value as a floating point number. This stored scale will later be used to initialize the layer's trainable weights. Overall, this setup lets the layer be created with a specific scaling factor that controls how its weights are initialized. In the build method, we first confirm that the input has at least 2 dimensions, so it is valid for this layer. We then read the size of the last dimension, which determines how many features we will scale. If this size is not positive, we raise an error because the layer cannot operate on such input. Next, we create a trainable scale weight, initialized with a constant value and shaped to match the last dimension, so each feature can be scaled independently. Finally, we call the parent class build method to finish setting up the layer. This function defines how the custom layer processes data during the forward pass. It first converts the input into a TensorFlow tensor, so it can use TensorFlow operations. It then checks that the number of dimensions of this tensor is known and raises an error if it is not, because the computation depends on that information. Finally, it multiplies the input tensor element by element with the layer's trainable scale weights, effectively scaling the input before sending it to the next layer in the model. This method saves the layer's configuration, so it can be recreated later with the same settings. It first calls the parent class method to get the existing configuration. Then it adds the initial scale value to this configuration, so that this custom parameter is also stored. Finally, it returns the complete configuration dictionary for serialization and later reconstruction of the layer. We begin by defining an input layer in Keras that expects each data sample to be a vector of 3 numbers. This means the model is designed to receive inputs with exactly 3 features. We also assign this input layer the name features, so it is easy to reference later in the model. Setting up this input layer is important because it establishes the data structure the model will use and ensures that all following layers receive data in the correct format. We apply our custom scaling layer by creating an instance of the previously defined scaling layer class and passing the input tensor to it. The layer is initialized with a scale factor of 0.5 and given a descriptive name for easier reference. When applied, this layer multiplies the input features by its trainable weights, so the input data is modified before it flows into the later layers of the model. We now add a dense layer to the model with a single output unit, so it produces one value for each input. This layer uses a linear activation, meaning it does not transform the output and can represent any real number. Such a setup is standard for regression tasks, where the goal is to predict a continuous value. The dense layer takes the scaled outputs from the previous layer, represented by X, and learns how to map these scaled inputs to the final prediction. We build the Keras model by calling the TensorFlow Keras model function with 2 main parts: the input layer we defined earlier, and the output from the dense layer that follows the custom scaling layer. We also assign the model a name, demo model, so it is easy to identify later. This step connects the input and output layers into a single complete architecture that is ready to be compiled and trained. The model is compiled using stochastic gradient descent as the optimizer, a standard method for training neural networks. It uses mean squared error as the loss function, which is appropriate for regression tasks because it measures how far predictions are from the true values. In addition, mean absolute error is tracked as a performance metric, providing the average size of the absolute differences between predicted and actual values during training. We define a small, fixed training dataset by creating a constant tensor in TensorFlow. This tensor has 2 rows and 3 floating point values in each row. The first row contains the numbers 1, 2, and 3, and the second row contains 0.5, 0, and -1. Using a constant tensor like this keeps the training data consistent and reproducible every time we run the code. We create a constant tensor in TensorFlow to hold the training labels, using a 2-dimensional array of 1s and 0s arranged so its shape matches what the model expects. The labels are stored with a data type of float32 to keep them compatible with the model's numerical operations. This tensor serves as the target output during training, allowing the model to learn how its inputs should map to these expected results. The model is trained using a fit procedure that adjusts its parameters to reduce the loss between its predictions and the target values. The training data includes input features and their corresponding targets. A model passes through the entire dataset 5 times, known as 5 epochs. With a batch size of 1, it updates its weights after each individual sample. The verbose setting is turned off, so no training progress messages are displayed. The code uses the model to generate predictions on the training data, turning off extra output during this step. This prediction phase is important because it lets us evaluate how well the model performs before we save it. By doing this, we can later compare these original predictions with the predictions made after loading the saved model from disk to ensure the model was stored and restored correctly. We are saving the entire model, including the custom layer, into a single file. This step preserves both the model's structure and its learned parameters. By doing this, we can later reload and use the model directly without having to recreate or redefine the custom layer. It ensures the model is fully reusable and ready for future inference or further training. Saving the model in the native keras format is important because it preserves the full model architecture, the learned weights, and any custom layers, such as the scaling layer defined earlier. Using this format ensures that the model can be reloaded later without losing any of its components. This makes it straightforward to continue training, reuse the model, or deploy it in other environments. To load a previously saved model in TensorFlow using keras, you specify the location of the saved model file. If the model uses a custom layer, you must also provide a mapping that links the custom layer's name, such as scaling layer, to its actual class definition. This mapping allows keras to correctly recognize and rebuild the custom layer when restoring the model. Without this step, the model could not be fully reconstructed. Next, we generate predictions using the loaded model by running the training data through it to produce outputs. Logging is turned off during this step, so no extra messages are printed. This prediction step is important because it lets us confirm that the loaded model behaves the same way as the original one. If the predictions match, it shows that the custom layer and its learned parameters have been correctly restored. This step prints the shape of the training data stored in the input array. By checking this shape, you can confirm the number of samples and features in your data. This helps you verify that the input has the expected dimensions before you continue. Ensuring the data is structured correctly at this stage can prevent errors in later model operations or analysis. We obtain the learned scale weights from the trained model by accessing the layer called the scaling layer through the model's layer retrieval method. After selecting this layer by name, we use its weight retrieval function to get the current values of its trainable parameters, which are the scale factors updated during training. We then print these values to inspect how the model has learned to scale the input features. We retrieve the scale weights from the loaded model by accessing the layer called the scaling layer to check that they were correctly preserved after saving and loading. Using the method that returns a layer's weights, we obtain these values and print them out. Comparing these weights before and after saving confirms that the model's parameters remain consistent across the save and load process. This verification step helps ensure the integrity of the model's state. We first print the model's initial prediction by taking the first value from the prediction output and converting it to a clear numeric format. This value is then displayed with a short descriptive message. Doing this lets us confirm what the model is predicting before we save and later reload it. It helps ensure that the predictions stay consistent throughout the entire save and load process. The script ends by printing the first prediction produced by the reloaded model to verify that saving and loading did not change its behavior. It takes the first value from the array of predictions and converts it to a simple floating point number for clear display. Matching this output with the original model's prediction confirms that the custom layer and its parameters were correctly preserved during the save and load process. This script shows how to create and use a custom layer in TensorFlow by subclassing the keras layer class. It defines a scaling layer with a trainable weight that multiplies the input, then builds a model using this custom layer followed by a dense layer. The model is compiled with stochastic gradient descent and mean squared error and trained briefly on a small dataset. Finally, the script saves and reloads the model, confirming that the custom layer and its learned weights are correctly preserved, because the original and reloaded models produce the same predictions. Managing trainable weights. When you build a custom layer, you must clearly define its trainable weights, such as the coefficients in a linear transformation or the filters in a convolution, because these are the parameters that change during training. A custom layer acts like a small model that turns inputs into outputs using these internal parameters. By explicitly declaring its weights, you ensure they are properly initialized, updated, saved, and restored. Good organization of these weights is essential for the layer to integrate smoothly into the overall deep learning workflow, whether the layer is a simple dense projection or a more complex attention mechanism. When working with trainable weights in a model, you must decide which parameters should be learned and which should remain fixed. For example, a custom normalization layer might learn scale and shift values while keeping mean and variance estimates non-trainable, and a recommendation system's attention layer might train some embedding matrices while freezing others. This separation controls what the optimizer can change, affecting both how expressive the layer is and how stable training remains. It is especially important when reusing or fine-tuning models, where you may train only specific adapter weights and leave the main parameters unchanged. When working with trainable weights, you should carefully choose their shape, initialization, and any constraints, because these decisions strongly affect how the model learns. The weight shape must match the input and output dimensions of the layer, so the intended transformation, such as a matrix multiplication or depthwise convolution, is valid. Initialization sets the starting point for optimization, and poor choices can lead to vanishing gradients or slow convergence, especially in deep networks. In some cases, adding constraints or regularization helps enforce properties like smoothness or sparsity. Managing these aspects thoughtfully helps your components fit well into training pipelines and perform reliably across different tasks. Python code, managing trainable weights. This script demonstrates how to manage custom layer weights in TensorFlow, highlighting the difference between trainable and non-trainable weights. It provides a simple example that shows how these two types of weights are defined and handled during model training. To follow the logic of the example, you are expected to run the cells in order so you can see how the weights are created and updated step by step. The line with the exclamation mark is a command to install TensorFlow version 2.20.0, which helps ensure the code uses the intended version for compatibility and reproducibility. Because this line is commented out, it will not run unless you remove the comment. It is often left this way as a reminder for users to install the required package if it is not already present in their environment. We start by importing TensorFlow and NumPy and giving them short, convenient names. TensorFlow is used to build and train machine learning models, while NumPy handles large, multi-dimensional arrays and matrices and provides many mathematical operations for them. Using brief aliases like tf for TensorFlow and np for NumPy is a common practice because it makes the code shorter and easier to read. This line displays the version of TensorFlow currently in use. It helps you quickly verify that your environment is running the expected version of the library. This check is important to ensure compatibility with your code and to make debugging easier when issues arise. To make code produce the same results every time it runs, we set deterministic seeds for the random number generators. We assign a seed value of 7 to TensorFlow's random module, so that its operations involving randomness are controlled. We also set the same seed value for NumPy's random module to control its random behavior. Using these fixed seeds ensures that any random numbers generated by these libraries are repeatable, which helps with reproducibility of experiments and results. This code defines a custom neural network layer called scaling layer that extends the standard Keras layer in TensorFlow. In its initialization, it sets up a scale parameter that can optionally be trainable, controlled by a Boolean setting named trainable scale. The initializer also accepts extra keyword arguments and passes them to the parent Keras layer setup. This design gives flexibility in deciding whether the scale value should be updated during training or kept fixed. When the build method runs, it uses the known input shape to set up the layer's weights. It reads the last dimension of the input as the feature size and checks that this value is positive, raising an error if it is not. It then creates a scale weight of that size, initialized to ones, and made trainable or not based on the layer's settings, and a bias weight of the same size, initialized to zeros, and always trainable. It also creates a running mean weight, initialized to zeros, but marked as non-trainable, so it is not updated during training. Finally, it calls the parent class build method to finish the setup. This function defines the forward pass of the layer by first converting the input into a TensorFlow tensor so it can use TensorFlow operations. When training is enabled, it computes the mean of the inputs across the batch and stores this value in a non-trainable running mean variable. It then scales the inputs by multiplying them element-wise with learned scale weights and adds learned bias weights. Overall, the layer outputs a scaled and shifted version of the inputs based on these learned parameters. We begin by defining an input layer that expects 3 features, which sets the shape of the data the model will receive. We then pass these inputs through a custom scaling layer, whose scaling factor is trainable, so it can be adjusted during learning to improve performance. Finally, we build the model by connecting the input and output through this scaling layer, creating a complete architecture that is ready to be compiled and trained with the scaling step built in. This code prints how many trainable weights the model has. It does this by looking at the model's list of trainable weights and counting how many items are in that list. The resulting number tells you how many parameters can be adjusted during training. This gives a quick sense of the model's size and complexity. This code prints how many non-trainable weights the model has. It looks at the model's list of weights that are not updated during training, counts how many items are in that list, and then outputs that number. This tells you how many parameters stay fixed, which helps you understand the balance between trainable and non-trainable parts of the model. We begin by creating a very small dataset using a numerical library. The input data is a two-dimensional array with one row containing the floating point values 1, 2, and 3, which serves as a simple set of input features. The target data is another two-dimensional array with one row containing the floating point values 2, 4, and 6, which represents the outputs we want the model to learn. Together, these input and target pairs form a basic training set that the model will use to learn how to map inputs to the correct outputs. Before training, the model is compiled by choosing how it will learn and what it will try to minimize. In this case, the learning method is stochastic gradient descent, a standard approach for updating the model step by step. The loss function is mean squared error, which calculates the average of the squared differences between predicted and actual values. Together, these choices define how the model adjusts its parameters and improves during training. The model is briefly trained using a fitting procedure that takes both the input data and the target data. Training runs for 20 epochs, meaning the model goes through the entire dataset 20 times. The training output is silenced by setting the verbosity to 0. This process is essential because it updates the model's trainable parameters, such as the scale and bias in the custom layer. After training the model, we examine the learned scale and bias parameters to see what values the model has settled on. We access the scale parameter from the custom layer inside the model and convert it to a numerical array so it is easier to inspect. We do the same for the bias parameter, turning it into a numerical array as well. Looking at these arrays shows the exact values the model adjusted during training. We summarize the parameters the model has learned by printing the scale and bias values. The scale values are rounded to 3 decimal places to give a clear, compact view of how these weights changed during training. We then do the same for the bias values, rounding them to 3 decimal places as well. Together, these rounded scale and bias values provide a concise snapshot of the model's learning progress. This example shows that the running mean variable in a custom layer stays non-trainable during training. The code reads the layer's running mean, converts it to a numeric array, and rounds the values for easier viewing. Because these values do not change, it confirms that the optimizer did not update the running mean. This behavior occurs because the variable was explicitly defined as non-trainable. This script shows how to handle trainable and non-trainable weights in a custom TensorFlow layer. It builds a scaling layer where the scale and bias parameters are updated during training, while a running mean is kept fixed. After setting the TensorFlow version and seeds for reproducibility, the custom layer is placed inside a simple model that is trained with stochastic gradient descent and mean squared error loss on a small dataset. When training finishes, the printed results reveal that scale and bias have changed, but the running mean has not, clearly illustrating the difference between trainable and non-trainable parameters. Using build versus init. When creating a custom layer, you should clearly separate what happens in the constructor from what happens in the build method. The constructor defines the layer's configuration, such as how many units it has and which activation function it uses, without depending on the input shape. The build method runs later, the first time real data passes through the layer, and uses the actual input dimensions to create the weight tensors. This separation keeps the layer flexible, and able to adapt to different input shapes while maintaining a clear design. In Keras, it is important to separate the constructor from the build method to support model reuse and flexibility. The constructor should store fixed design choices, while the build method creates the actual weights. What's the real input shape is known at runtime. This is especially useful for models that handle variable sequence lengths or different image resolutions. By centralizing variable creation in the build method, layers can adapt to incoming data shapes, and Keras can manage the weights cleanly and consistently. When building custom Keras layers, avoid creating variables in the constructor if their shapes depend on the input data, because this makes the layer fragile and hard to reuse. This pattern can break important Keras features, such as model cloning and serialization, and may cause failures when inputs change, like an attention layer that only works for one fixed input size. Instead, create such variables in the build method so the layer can adapt to the actual input shape. In practice, keep the constructor free of input-dependent logic, and use the build method to create weights tied to specific input shapes, which leads to more robust and reusable layers. Python code using build versus init. This script gives a clear explanation of the difference between the build and init stages in a model. It uses a custom dense layer as an example to show how these stages work in practice. The script compares their behavior and prints out the shapes of key tensors. This helps you see when and how the layer structure is created during the model's lifecycle. The commented line recommends installing TensorFlow version 2.20.0 to match the code. Using this exact version helps avoid problems caused by differences in how other versions work. Specifying library versions like this is a common way to keep behavior consistent across different systems and environments. We begin by importing TensorFlow because it is the core library we use to build and train our machine learning models. TensorFlow offers a full deep learning ecosystem that lets us define and work with tensors, construct neural network layers, and run computations efficiently. By bringing it into our script, we gain access to all of these essential tools and functions. This import step is therefore crucial for carrying out the tasks planned in this code. We use TensorFlow's random module to set a fixed random seed so that any random operations in our code always produce the same results. This is important for reproducibility when building machine learning models. By controlling the randomness, we can reliably repeat experiments and verify that our results are consistent over time. This line of code displays the version of TensorFlow that is currently in use. It provides a quick check of which release of the library is loaded. Confirming the version helps ensure that your code is compatible with the installed TensorFlow features and behavior. We define a custom dense layer by creating a class that inherits from the Keras layer in TensorFlow. In its constructor, we set up the layer's configuration, including the number of units, which controls the output size, and whether to include a bias term, which is true by default. Any extra settings are passed to the parent class using the supercall, so they are handled correctly. This initialization ensures the layer's configuration is stored properly and is ready to be used when the layer is later built and applied to data. In the build method, we first read the last dimension of the input shape to know how many features the input has, since this determines the size of the weight matrix. We then create a weight matrix called the kernel, whose shape matches the number of input features and the number of units in the layer. If the layer is set to use a bias term, we also create a bias vector with one value per unit. Otherwise, the bias is left undefined. Finally, we call the parent class build method to complete any remaining setup for the layer. Inside the call method, the custom dense layer carries out its forward pass by multiplying the input tensor with the layer's weight matrix using TensorFlow's matrix multiplication. If a bias term has been defined, it is then added to this product. The final result of these operations is returned as the output of the layer, representing the transformed version of the input data after passing through the dense layer. This code defines a custom layer class called myDenseInit that extends the standard TensorFlow layer class. In its constructor, it calls the parent constructor, stores the number of units, and tries to guess the input dimension, saving these as internal variables. It then creates a weight matrix based on this guessed input size and the number of units. However, this design is flawed because it assumes the input shape too early, which can cause errors if the actual input shape turns out to be different. In this part of the code, the build method for the custom dense layer class does not actually do any work because the weights were already created in the constructor. The method only calls the parent class's build method to ensure any standard setup still occurs. This pattern reveals a misuse of weight initialization since it skips the dynamic setup that the build method is designed to handle. As a result, the code does not follow the intended lifecycle for creating and configuring layer weights. In the call method, the layer takes an input tensor and multiplies it by the weight matrix that was set up earlier. This matrix multiplication computes the dot product between the input and the weights. Through this operation, the learned transformation is applied to the input data. The result of this multiplication is then returned as the output of the layer. We create a tensor filled with ones shaped as 2 by 4 and using the float32 data type. This tensor represents input data with 4 features. It is used to test how different layers process inputs with this specific number of features and dimensions. We create a new input tensor called inputs3, which is filled with ones and has a shape of 2 by 3, meaning 2 samples with 3 features each. Its data type is float32, a common choice in TensorFlow because it balances precision and performance. This input setup is used to test how different layers handle inputs with this feature size, especially when comparing layers that create their weights using a build method versus those that do so in their initialization method. We create an instance of the custom dense layer class called myDenseBuilt, configured with 5 units, so it produces 5 output features for each input. The layer is set to use a bias term, which gives the model more flexibility when fitting the data. With this setup, the layer is ready to be placed in a neural network and will automatically build its internal weights the first time it processes input data. When we pass an input tensor with 4 features into the custom dense layer called myDenseBuilt, this call activates the layer's build method. The build method uses the input shape to create and initialize the layer's weights. After this step, the layer is fully set up and ready to carry out its forward computation on the given inputs. We test the previously defined layer by calling it with a new input tensor that has 3 features to see if it can handle a different input shape. If this call works, we save the output and record that no error occurred. If an exception happens instead, we capture the error message as text and store it, while setting the output to none to indicate that the operation failed. We create an instance of a custom layer class called myDenseInit that is intentionally designed to guess the input dimension when initializing its weights. We set the layer to have 5 units, so it will produce 5 output features for each input. We also give it a guessed input dimension of 4, meaning it expects 4 features in the input data. This example is used to show the problems that can arise when the input dimension is guessed instead of being determined dynamically during the build process. We apply the incorrectly initialized dense layer to an input tensor whose shape matches the input dimension that was assumed when the layer was created. Because these dimensions line up, the layer can perform a normal forward pass. In this pass, the input tensor is multiplied by the layer's predefined weights. The operation succeeds without errors and produces an output, since the input and weight shapes are compatible. We test the incorrectly initialized layer by giving it input with a shape that does not match what it expects. If the operation works, we save the output so we can inspect it. If it fails, we catch the exception and save the error message instead. This lets us handle shape mismatches safely and observe how the layer responds to unexpected input dimensions. We print the shape of the kernel weight matrix from the correctly built custom dense layer to confirm how it was created. This shape tells us the dimensions of the weight matrix that the layer uses. By examining these dimensions, we gain insight into how the layer is configured and how it will process the input data. We now check the shape of the output produced by our custom dense layer when it processes an input tensor with 4 features. This shows how the layer transforms the input and lets us verify that the resulting output shape is correct. Matching the expected shape confirms that the layer uses the number of units specified when it was initialized and is behaving as intended. This code checks how the layer responds when given a second input tensor that has 3 features and then prints the resulting output shape. It uses a helper function to safely read the shape information so that if the layer returns no output, the program does not crash. Overall, it shows that the layer can automatically adjust to different input shapes without needing manual changes. We first print a message to indicate that we are checking for errors when using inputs with 3 features on the correctly built layer. This prepares the listener for the result of the test. Next, we print the captured error message if using the layer with a mismatched input size caused a failure. If no error occurred, we instead print a simple message saying that no error was raised. Together, these messages tell us whether the layer handled the change in input size correctly or not. We print the shape of the kernel weight matrix for the layer that was initialized incorrectly to see the actual dimensions of its weights. This reveals how the layer was set up using a guessed input size instead of being built dynamically from real input data. By checking these dimensions, we can more easily spot and diagnose problems caused by mismatched input shapes in the model. We examine the output shape of a dense layer that was initialized incorrectly, focusing on the case where the input dimensions happen to match the layer's guessed dimensions. When this alignment occurs, the layer produces an output with the expected shape. This confirms that the layer can process the input correctly as long as the input shape matches its assumed configuration, despite the flawed initialization. We now test whether using a layer with an incorrect guessed input size causes an error when given mismatched data. Specifically, we apply inputs with 3 features to a layer that was initialized assuming 4 input features. We then print a message indicating whether this mismatch triggered an error, allowing us to confirm how the system responds to incompatible input dimensions. The code checks whether an error message was produced by a previous operation and reports the result. If an error message exists, it is displayed so you know what went wrong. If no error is found, the code instead reports that no error was raised. This gives clear feedback on whether the operation succeeded or failed. This script compares 2 ways of defining custom layers in TensorFlow. One that uses the build method correctly, and one that misuses the initialization method, pause. The properly designed layer creates its weights during the build phase based on the actual input shape, so it can handle inputs with different numbers of features without errors. Pause. In contrast, the incorrect layer guesses the input dimension during initialization, which makes it work only for the specific input size it assumed. Pause. As a result, it processes inputs with 4 features, but fails when given inputs with 3 features, because the weight dimensions no longer match. Pause. By printing the shapes of the weights and outputs, the script highlights how using the build method makes custom layers flexible, while relying on initialization for input dimensions leads to rigid and error-prone behavior. Designing custom losses. Function-based losses. Function-based loss functions are used to guide how a model learns by turning its predictions and target values into a single number that measures error, which the optimizer then tries to minimize. By designing this loss carefully, you can emphasize some types of mistakes over others, such as penalizing misdiagnoses more than false alarms in medical tasks, or prioritizing ranking accuracy in recommendation systems. This allows the training process to align the model's behavior with the specific goals of the application instead of relying on a generic objective. In modern deep learning, a loss function should work on batches of predictions and targets so training is efficient. And it must be mostly differentiable with respect to the model's outputs so gradients can update the weights. It should combine the individual losses in a batch into a single value, typically by averaging or summing them. In financial forecasting, a custom loss can be designed to penalize underestimates more than overestimates, encouraging conservative predictions that are useful in areas such as insurance or credit scoring. Function-based loss terms let you go beyond simple error measurement and embed extra information or constraints into training. In energy forecasting, you might add a loss term that penalizes rapid changes in predictions to encourage smoother, more realistic outputs. In content moderation, you can combine a standard loss with an extra penalty for uncertainty in sensitive cases, pushing the model toward clearer decisions. By designing these custom losses, you define what good behavior means for your model, while keeping them compatible with your usual training and evaluation process. Python code. Function-based losses. This script demonstrates how to define and use custom loss functions in TensorFlow Keras. It works with a small set of dummy data, so you can focus on understanding how the custom losses are implemented rather than on achieving high model performance. The main goal is to clearly show the structure and usage of these custom losses in a simple, controlled setting. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Using this exact version makes sure the script runs with the intended library setup. This is important for compatibility because different versions can change how features or functions behave. It also supports reproducibility, so others can run the same code and get consistent results. We begin by importing several key libraries used in many machine learning projects. The operating system library lets us work with files and environment settings. The random library provides tools for generating random numbers and making random choices. We then import NumPy for efficient numerical computations with arrays and matrices. Finally, we bring in TensorFlow, which includes Keras, to build and train neural network models. To make the training process consistent and reproducible, we set a fixed seed value, often chosen as 42. We apply this seed to Python's random number generator, then to NumPy's, and finally to TensorFlow's, which controls randomness in tasks like initializing neural network weights. Using the same seed each time ensures that all random numbers, and therefore the training results, are identical whenever the code is run. This reproducibility is important for debugging models and verifying experimental results. This line checks and prints the version of TensorFlow that is currently in use. It provides a quick way to verify that the environment is running the expected version. Confirming the version is important because the rest of the code may rely on specific TensorFlow features or behaviors. Ensuring the correct version helps avoid compatibility issues during development or execution. The code uses TensorFlow to check whether any GPU devices are available. If it finds at least one GPU, it sets the device to GPU, so computations run there for better performance. If no GPU is found, it falls back to using the CPU instead. This setup helps ensure the model automatically uses the most efficient hardware available for training and inference. This code checks whether a physical graphics processing unit is available, and then reports which type of device will be used for computations. If at least one graphics processor is found, it selects that as the device. Otherwise, it falls back to the central processing unit. It then prints this choice so the user knows whether TensorFlow operations will run on a graphics processor or on the main processor. We create a small synthetic dataset for a regression task by first choosing 64 samples. We then generate input values as evenly spaced numbers between -1 and 1 and reshape them into a column of data. To make the dataset more realistic, we add random noise drawn from a normal distribution and scaled down by a factor of 0.1. This noisy input data provides a simple but practical dataset for training a regression model. We generate the target values in our dataset using a simple linear rule. For each input, we multiply it by 2 and then add 0.5. This creates a clear linear pattern between inputs and targets. To make the data more realistic, we then add a small amount of random noise to each target value. This noise represents the kind of measurement variation we often see in real-world data, where values are not perfectly precise. Before building the model, the code first checks that the input and target data have the correct shapes. It confirms that the input data has one column per sample, meaning each sample contains a single feature. It also verifies that the target data has one column per sample, so each target is a single value. These assertions help catch shape mismatches early and prevent errors during model training. Mean squared error is a common loss function used in regression tasks to measure how well a model's predictions match the true values. To compute it, we take the difference between each true value and its predicted value, square these differences to get the squared errors, and then average them across the batch using TensorFlow's reduce mean operation. The result is a single number, where smaller values indicate that the model's predictions are closer to the true values and therefore performing better. This custom loss function is designed to penalize underestimates more strongly than overestimates. It first computes the difference between the predicted and true values. Then it builds one mask that marks where the prediction is less than the true value, and another mask for where the prediction is greater than or equal to the true value. Using these masks, the function can apply different penalty strengths depending on whether the model is underestimating or overestimating the target. This code defines a custom loss function that penalizes underestimates more than overestimates. When the model's prediction is lower than the actual value, the error is given a weight of 3, making these mistakes more costly. When the prediction is higher than the actual value, the error is given a weight of 1, so overestimates are treated less severely. These weights are applied to the squared differences between predicted and actual values using TensorFlow's square operation to produce a weighted error that guides model training. This function computes the average of the weighted errors across the entire batch using TensorFlow's reduce mean operation. By taking this mean value, it produces a single number that represents the overall loss for that batch. This loss value is then used during training, so the model can adjust its parameters to reduce the error over time. We build a simple sequential model in TensorFlow Keras by stacking layers in order. It starts with an input layer that takes data with one feature, which defines the input shape. Then we add a dense layer with 8 neurons using a ReLU activation to learn nonlinear patterns from the input. Finally, we include a dense output layer with a single neuron, which produces a continuous value suitable for regression tasks. The model is being prepared for training by choosing specific settings. It uses the Atom optimizer, which is well suited for efficient learning, with a learning rate of 0.05 to control how strongly the weights are updated. A custom loss function, called asymmetric underestimate loss, is applied, so that underestimating is penalized more than overestimating, matching the model's goal. In addition, mean squared error is tracked as a metric to provide a baseline measure of how far predictions are from the true values. Together, these choices configure the model to focus on minimizing the custom loss while monitoring overall prediction error. The model is trained using the fit function in TensorFlow Keras, which uses the input data and true target values to update the model's weights. Training runs for 40 epochs, so the model goes through the entire dataset 40 times. The data is handled in batches of 16 samples at a time. The training is set to run silently, with no progress messages printed during the process. The code evaluates the trained model on the same small dataset it learned from, and it does this without printing anything during the process. The evaluation produces 2 numbers, a custom loss value and a mean squared error value. These results are stored for later use and indicate how well the model's predictions match the actual target values. This step provides a quick check of how effectively the model has learned from the training data. To generate predictions for inspection, we first create a small test input array with the values -0.5, 0, and +0.5, and set its data type to float32 so it works smoothly with TensorFlow. We then pass this array to the model's prediction function to obtain the corresponding outputs. The prediction call is configured with no extra logging, so it runs silently and only returns the prediction results. The code prints a brief summary of the model's training performance. It first reports the value of a custom asymmetric loss, which penalizes underestimates more than overestimates, and shows how well the model performs under this specific criterion. It then prints the baseline mean squared error, a standard measure of accuracy based on the average squared difference between predictions and true values. Together, these 2 numbers help compare the model's performance under the custom loss with its performance under a conventional error metric. The code first prints the test inputs in a simple one-dimensional form, so the values being tested are easy to read. It then prints the model's predictions in the same one-dimensional format for clear comparison. Finally, it computes the ideal target values for these inputs using the linear rule that each output should be 2 times the input plus 1/2, and prints those as well. Seeing the inputs, predictions, and ideal targets side by side helps you quickly judge how closely the model's predictions match the expected linear relationship. The model is first saved to a file so that its architecture and learned weights are stored, but the optimizer state is left out, which makes later loading simpler. After saving, the model is loaded back from this file. During loading, you must provide a dictionary that maps the names of any custom loss functions to their actual implementations. This step is essential because TensorFlow does not automatically know about custom losses, and without explicitly specifying them, the reloaded model would not work correctly. To check that the reloaded model behaves the same as before, it is evaluated on the same dataset using the input data and true targets. During this evaluation, the model computes the loss and the mean squared error with the previously defined custom loss functions, while output is suppressed. Afterward, the loss and error values are printed and compared. Matching results confirm that saving and loading did not change the model's performance, and that the custom loss functions were correctly preserved. This script shows how to use custom loss functions in TensorFlow Keras with a simple regression model. It creates a small synthetic dataset with noisy inputs and linearly related targets, then defines two losses: standard mean squared error and an asymmetric loss that penalizes underestimates more than overestimates. The model is compiled with the custom asymmetric loss, trained briefly, and then evaluated on the same data using both the custom loss and mean squared error. It also generates predictions on test inputs and compares them to ideal targets. Finally, the model is saved and reloaded to confirm that the custom loss remains compatible and produces consistent evaluation results. Loss classes with call. When you need more structure than a simple loss function, you can define the loss as a class with a call method. This creates an object that behaves like a loss function, but can also store configuration, track internal state, and organize helper logic. The call method describes how to compute the loss from model outputs and targets, while the constructor lets you adjust how the loss behaves. For example, you can change how sensitive it is to large errors or adapt it for classification versus regression. This object-oriented approach makes complex loss definitions easier to reuse, test, and understand. Defining your loss as a class with a call method fits smoothly into the training workflow and makes serialization, configuration, and logging more reliable. The loss becomes a clear, self-contained object whose settings can be easily saved and restored with the model. This is especially important when training and deployment happen in different environments, such as in healthcare or finance, because it preserves custom parameters and internal logic over time. In contrast, a simple function-based loss usually lacks a well-defined, serializable configuration, and it's harder to manage consistently across systems. Defining a loss function as a class with a call method allows it to do more than a fixed calculation. It can track statistics such as a moving average of errors, and change how the loss behaves over time. In recommendation systems, this can help emphasize underrepresented users, and in robotics, it can adjust safety margins based on recent performance. This design keeps the training loop simple, since the model, optimizer, and loss still fit together cleanly, while the more complex loss logic stays inside a reusable component. Python code. Loss classes with call. This script demonstrates how to define and use a custom loss class, with special attention to how the call method is implemented and invoked during training. The example keeps the training process very small and simple, so the focus stays on the loss behavior. It also keeps the printed or logged output short, making it easier to see how the custom loss is applied in practice. The commented line recommends installing TensorFlow version 2.20.0 to match the code used in this script. Using this specific version helps avoid problems that can occur when different TensorFlow versions change features or syntax. It is a setup step to ensure the programming environment is correctly configured before running the script. We begin by importing three key tools. The operating system module lets our program interact with the computer's system, such as working with files. The random module allows us to generate random numbers, which is useful for creating random data or controlling randomness with a seed. Finally, we import NumPy, a numerical computing library that provides efficient arrays and many mathematical functions for data processing. We start by importing TensorFlow, a main library used to build and train machine learning models. Within TensorFlow, we use Keras as a high-level interface that makes creating neural networks easier. We then import the layers tools from Keras, which give us components like dense layers that we use to design the structure of our models. We set a seed value of 42, so that all random operations in our code give the same results every time it runs, which is important for reproducible machine learning experiments. First, we set the seed for Python's built-in random number generator, then for NumPy's random generator, and finally for TensorFlow's random generator. This makes random numbers, weight initialization, and other stochastic behavior consistent across runs. Such deterministic behavior is especially helpful for debugging and for reliably comparing different experiment results. This line displays the version of TensorFlow currently in use. It provides a quick check that your environment is set up as expected and matches the version you intend to work with. Confirming the version helps ensure that your code is compatible with the installed library. It is especially useful when you rely on specific features or when you are debugging issues that may be caused by version differences. We create a custom loss class called scaled MAE loss that extends the standard keras loss class and introduces a scale hyperparameter, which defaults to 1 and lets us control how strongly the loss contributes during training. In the initializer, we also assign the loss a descriptive name and use a reduction method that sums the loss over the batch size, a common way to combine individual losses into a single value. The parent class initializer is called to ensure everything is set up correctly, and the scale value is converted to a TensorFlow tensor with a float32 data type so it works smoothly with TensorFlow operations. The call method first converts the true and predicted values into TensorFlow tensors with a float32 data type, so they are ready for computation. It then checks that both tensors have the correct column vector shape to catch any mismatched dimensions early. After this, it computes the mean absolute error by averaging the absolute differences between the true and predicted values. Finally, it multiplies this error by a scale factor set during initialization and returns the scaled loss, allowing the overall loss magnitude to be adjusted as needed. We create a small synthetic dataset for a regression task by first choosing 64 samples. The input values are generated as evenly spaced numbers between -1 and 1, stored with standard floating point precision. To make the data more realistic, we add a bit of randomness using noise drawn from a normal distribution and scaled to a small value, then stored with the same precision. This combination of structured inputs and slight noise simulates real-world data with natural variation. We create the target values for our regression task using a simple linear rule. Each input value is multiplied by 2, then we add 0.5. To make the data more realistic, we add a small amount of previously generated noise. Finally, we reshape the results into a column vector so they are compatible with the expected input format of the keras model. The code reshapes the input values into a two-dimensional array with a single column, so they match what keras expects. Dense layers in keras require input features to be organized in this format. This reshaping makes sure each data point is treated as its own sample with one feature. As a result, the data aligns correctly with the model's input requirements. We build a simple sequential model in keras by stacking layers in order. First, we define an input layer that takes data with a single feature, which sets the expected input shape. Then we add a dense layer with 8 neurons using the ReLU activation function so the model can learn nonlinear patterns from the input. Finally, we include a dense output layer with 1 neuron, which produces a single, continuous value suitable for regression tasks. We create an instance of a custom loss class called scaled MAE loss and set its scale factor to 2. This means the mean absolute error is multiplied by 2 when the loss is calculated. By scaling the loss in this way, we change how strongly it influences the model's training. In effect, we amplify the error signal by the chosen factor, so it has a greater impact on updating the model. The model is now being compiled, meaning it is being set up for training. It uses the Atom optimizer, which is efficient and adapts well to different learning rates. The loss function is a custom version of mean absolute error that is multiplied by 2, allowing the training process to be tailored to specific needs. During training and evaluation, the model also tracks mean absolute error as a metric to provide a clear measure of prediction accuracy. The model is trained using the fit method, which takes the input features and target values and runs for 10 epochs, meaning it passes through the entire dataset 10 times. It uses a batch size of 16, so it updates its weights after processing 16 samples at a time. The verbose setting is 0, so the training runs without printing progress updates. This configuration provides a quick and quiet training process, which is useful for testing or when you want to avoid extra output. The code evaluates the trained model using the test data by comparing its predictions with the true target values. From this comparison, it computes 2 metrics, the loss and the mean absolute error. The evaluation function returns these metrics, which are then stored for later use or analysis. During this process, detailed output is turned off, so the evaluation runs quietly. The code reports the model's final performance by printing the scaled loss value and the mean absolute error, each converted to a simple numeric value. The scaled loss summarizes how well the model optimized the custom loss function during training. The mean absolute error then gives a clear measure of how close the model's predictions are to the true target values. Together, these two outputs provide a concise overview of the model's effectiveness. The code saves the trained model to a file named custom-loss-model.keras. It stores only the model's architecture and learned weights, without the optimizer's state. This means the model can be loaded later for deployment or sharing, without including training details. As a result, others can use the model directly without needing to retrain it. To load a previously saved model in Keras, you use the load model function and give it the path to the saved file. If the model uses a custom loss function, you must also provide a mapping of custom objects so Keras knows how to rebuild it. In this case, you pass a dictionary that links the name of the custom loss class, called scaled MAE loss, to the class itself. This allows Keras to correctly reconstruct the model with its custom loss function when it is loaded. The code checks that the loaded model still works correctly by running an evaluation step on it. It calls the model's evaluate function with the input data and the corresponding target values. This evaluation computes 2 main metrics for the dataset, the loss and the mean absolute error. The process is run in silent mode, so it does not print progress messages. The resulting loss and mean absolute error values are then stored and used to confirm the model's performance after loading. We first print the loss value of the loaded model to confirm it matches the expected result, showing that performance is consistent after saving and loading. We then print the mean absolute error to check that the model still predicts target values with the same level of accuracy. Finally, we print the scale attribute from the custom loss class to verify that the scaling factor used during training has been preserved, ensuring the loss is computed as intended. This material explains how to create and use a custom loss class in TensorFlow by defining a call method. It introduces a scaled mean absolute error loss, which multiplies the usual mean absolute error by a chosen factor. A simple regression model is trained on a small synthetic dataset with a linear pattern and noise using this custom loss. After training, the script evaluates the model, reporting both the scaled loss and the standard mean absolute error. Finally, it saves and reloads the model to show that the custom loss configuration is preserved and that the reloaded model produces consistent evaluation results, demonstrating how to implement, apply, and persist custom loss functions in TensorFlow. Loss reduction and masking. When designing a custom loss for a deep learning model, you must define both the error for each prediction and how these errors are combined across the whole batch. This combining step, called loss reduction, turns many individual losses into a single value used for optimization. In common tasks like image classification, losses are usually averaged, but in specialized problems such as fraud detection, you might instead sum them or apply weights to highlight certain examples. Choosing the right reduction method ensures that training reflects the real priorities and constraints of the problem you are solving. Masking is important in loss calculation because it controls which data points are actually used when computing the loss. In tasks like natural language processing, sentences are often padded to the same length, and this padding must be ignored so the model does not learn from meaningless tokens. The same idea applies to data with missing values, such as sensor readings or medical records, where only valid entries should influence learning. A well-designed custom loss function respects these masks, so the model focuses on relevant data and is not distracted by padding or missing values. When you design a custom loss function, it must fit smoothly with the rest of the training process, including built-in layers and metrics. You need to correctly handle masks from earlier layers so the model is not penalized for irrelevant data, which can slow learning or hurt performance. You also need consistent reduction strategies so the training loss and metrics match and gradients are not distorted. Carefully treated masking and reduction is especially important in areas like recommendation systems and speech recognition, where it helps avoid overfitting and leads to a more robust training setup. Managing custom metrics. Metric state variables. When creating a custom metric, it is important to understand metric state variables, which act as the metric's memory. These variables accumulate information across batches or an entire epoch, such as running totals and counts. At the end of the process, they are combined to produce the final metric value that appears in your logs. For example, to track average absolute error in a regression model, one state variable can store the sum of all errors, while another stores how many predictions were made. This design lets the metric provide meaningful, up-to-date feedback during training or evaluation. State variables in custom metrics are special objects integrated with deep learning frameworks, not just ordinary Python variables. They are managed so they run on the correct device, such as a CPU or GPU, and can take part in automatic differentiation when needed. These variables are tracked and saved along with the model's weights and configuration, so metric values can resume correctly after a pause or restart. This makes metrics consistent and reliable across restarts or distributed training, which is especially important for long-running tasks like fraud detection. Metric state variables are the internal values a model uses to keep track of metrics during training, validation, testing, and inference. When you define a custom metric, the framework automatically manages these variables so they are correctly initialized, updated, and stored. This is especially important in production, where you may need to monitor performance over time, such as the accuracy of a recommendation system as new data arrives. Proper handling of metric state variables also ensures that when a model is exported and later reloaded, the metric state can be accurately reconstructed. Understanding how these variables are managed is essential for making custom metrics work reliably across saving and loading models. Python code, metric state variables. This script demonstrates how metric state variables work in practice. It uses a very small model together with a custom metric, so you can clearly see how the metric's internal state is managed. The main goal is to show how to correctly save the metric state during training and then load it again later, preserving its values across runs. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It makes sure the code uses this exact version so that its behavior and compatibility are as expected. This is important because different TensorFlow versions can change features or introduce bugs. Such a command is typically used when TensorFlow is not already installed, or when the code depends on that specific version to run correctly. The script begins by importing 3 key libraries. It brings in the operating system library to work with files and directories, NumPy for efficient numerical operations and array handling, and TensorFlow for building and training machine learning models. Together, these imports provide the core tools the script needs to manage data and construct models. We set a deterministic seed, such as 123, so that any random operations in our code give the same results every time. We apply this seed to the random number generator in NumPy, so its random values are repeatable. We also set the seed for TensorFlow's random number generator, so that operations like initializing neural network weights are consistent across runs. This reproducible setup is important for reliable debugging and for fairly comparing results between different executions of the script. This line displays the version of TensorFlow currently in use. It helps you quickly confirm that your environment is set up correctly. Checking the version is important to ensure that your code is compatible, especially when relying on features or functions that may change between TensorFlow releases. We create a custom metric class called running mean absolute error by extending TensorFlow's metric base class. During initialization, it defines 2 state variables, one that stores the running total of absolute errors and another that counts how many samples have been processed. Both are initialized to 0 using TensorFlow's built-in method for creating metric weights. These 2 values are then used together during training to compute the running mean absolute error. The method first converts the true and predicted values to a consistent float type and checks that they both have the correct column vector shape. It then computes the absolute error by taking the absolute difference between the true and predicted values and sums these errors to get the total error for the batch. The number of elements in the batch is determined and converted to a compatible float type. Finally, the method adds the batch error and batch size to running totals, allowing it to accumulate information over many batches and maintain a running mean absolute error. This function computes the final value of a custom metric by taking the total absolute error and dividing it by the number of observations. It uses a TensorFlow division operation that avoids producing not a number results when the count is 0. This ensures the metric remains safe, stable, and reliable, even in edge cases where no data points are available. This method resets the internal state of the custom metric, so it can start fresh for a new training epoch. It sets the total absolute error back to 0, clearing any previously accumulated error. It also resets the count to 0, removing any prior sample information. This reset is essential to keep metric calculations accurate and independent across different epochs. We create a small synthetic dataset for a regression task by generating 64 input points evenly spaced from -1 to 1 and reshaping them into a single column. To make the data more realistic, we add a small amount of random noise drawn from a normal distribution. The target values are then computed by taking each input, multiplying it by 2, adding 0.5, and including the noise. This produces data that follows a simple linear relationship with some randomness, which is well suited for training and testing a regression model. We build a minimal Keras sequential model as a simple stack of layers, where each layer passes its output to the next. The model starts with an input layer that takes data with a single feature, defining the input shape. We then add a dense layer with 4 units and a ReLU activation, which learns 4 transformed features from the input and introduces nonlinearity. Finally, we add a dense output layer with 1 unit that produces a single numeric prediction, making this model suitable for regression tasks. The model is now being compiled, which means it is being set up for training. It uses the Atom Optimizer, a common and efficient choice for handling sparse gradients. The loss function is mean squared error, which is standard for regression because it measures the average squared difference between predictions and true values. In addition, a custom running mean absolute error metric is used to track the average absolute error over time, providing a more interpretable view of the model's performance than the loss alone. We train the model using the fit method, which takes the input data and the target data and runs training for 3 full passes over the dataset. The data is processed in batches of 16 samples at a time. Training is run in silent mode, so no progress messages are printed. This short training run is enough to update the internal state of our custom metric, allowing it to track the running mean absolute error as the model learns. After training the model, we evaluate our custom metric called running mean absolute error. We retrieve its final value by looking up this metric in the training history and taking the last recorded entry. This gives us the model's most recent performance according to the custom metric. We then print this final value before saving the model, so we have a clear reference for how well it performed. The code saves the trained model to a file, including the setup for the custom metric. It first defines a name for the file where the model will be stored. Then it calls the model's save function, which writes the model's structure, learned weights, and custom settings such as the custom metric into that file. This allows the model to be reloaded later with all its original behavior and custom components preserved. To reuse a previously saved model in TensorFlow, you load it by giving the load model function the path to the saved file. When the model includes custom components, such as a custom metric class called running mean absolute error, you must also pass a dictionary that maps the metric's name to its class. This tells TensorFlow how to rebuild that custom metric during loading. Doing this is essential to preserve the full functionality of the model, including all its custom parts. After loading the model, we run an evaluation to confirm that the custom metric still works correctly. We use the same input and output data as in training, so the results are comparable. The data is processed in batches of 16 examples at a time, and detailed logging is turned off to keep the evaluation quiet. The results are returned as a dictionary, so we can easily look up each metric by name. After loading the model, we check the value of the custom metric to make sure it has been restored correctly. This confirms that the metric's internal state matches what it was before the model was saved. We do this by looking up the metric's value in the results returned by evaluating the loaded model. If the value is present and correct, it verifies that the custom metric still works as intended after loading. We begin by creating a variable to store our custom metric and set it to none. Then we loop through all the metrics in the loaded model and check each one to see if it is an instance of our custom running mean absolute error class. When we find this specific metric, we save it in our variable and stop the search. This gives us direct access to that custom metric inside the loaded model, so we can later examine its internal state values. The code first checks whether the loaded metric instance is available. If it is, it prints the total absolute error and the number of samples processed, converting both to floating point values for easier reading. This output lets you confirm that the metric state was correctly preserved when the model was loaded. If the metric instance is missing, the code instead prints a message explaining that the custom metric was not found, alerting you to a potential loading issue. This script shows how to use a custom metric in a TensorFlow model and preserve its state when saving and loading the model. It builds a simple regression dataset and neural network, then defines a custom running mean absolute error metric that tracks mean absolute error across batches. The model is trained briefly, so the metric's internal state variables are updated, and then the entire model, including the metric configuration, is saved. After reloading the model, the script evaluates it again, prints the metric value, and inspects the metric's internal state to confirm that the saved state was correctly restored. Overall, it demonstrates how to maintain custom metric states across model serialization in TensorFlow. Updating and reading metrics. Once you define the internal state for a metric, the main job is to keep this state updated during training, and then read it out for reporting. Updating means combining the model's predictions and targets with the existing state, so it reflects all data seen so far, such as adding new errors to a running total and counting how many samples were processed. Reading the metric then converts this internal state into a clear value, like a single floating point number for logs or dashboards. This separation lets metrics collect data incrementally while still providing a stable, easy-to-interpret value for evaluating performance. During model training and evaluation, metrics are updated and read automatically, but understanding how they work helps you design custom metrics that behave as expected. At each training step, the metric updates its internal state using the latest predictions and true labels, then reports a performance value so far that can be logged or monitored. For example, a sensitivity metric in medical imaging keeps running counts of true positives and false negatives and reports their ratio. Similar cumulative, incrementally updated metrics are widely used in areas like fraud detection and recommendation systems, where clear reporting of these running statistics is essential. When working with custom metrics in larger models, it is important that their internal state is saved, loaded, and resumed correctly, so they update and report values consistently. Because the metric state is stored in dedicated variables, saving and loading the model should also preserve the metric's progress, allowing training to pause and resume without breaking logs or performance tracking. This is especially critical in long-running tasks, such as autonomous driving, where metrics that track critical failures must continue accurately after a restart. To achieve this, the metric's update logic must be deterministic, and the relationship between its stored state and reported value must remain stable, so it integrates reliably with experiment tracking and deployment monitoring workflows. Python code, updating and reading metrics. This script demonstrates how custom metrics behave during model training. It shows how to update metric values, read them as training progresses, and then use those metrics effectively. It also walks through saving a trained model and loading it again, so you can preserve and reuse both the model and its associated metrics. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It forces the environment to use this exact version, so the code runs with the expected features and interfaces. This is important for compatibility, since different versions of TensorFlow can change how certain functions work. Such a command is typically executed in a Jupyter notebook or a similar environment that allows direct shell commands. We start by importing 3 key libraries. The operating system library lets us interact with the system for tasks like working with files and environment settings. The random library is used to generate random numbers, which can help create random data or initialize values. Finally, the numerical computing library NumPy provides efficient tools for handling arrays, and performing fast mathematical operations. We start by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we use Keras as a high-level interface that makes it easier to build and train neural networks. From Keras, we then import the layers tools, which let us design the structure of a neural network by stacking different kinds of layers, such as dense or convolutional layers. We set a seed value of 42 so that our code produces the same random results every time it runs. This seed initializes the random number generators used by Python's random tools, by NumPy, and by TensorFlow. When these seeds are fixed, any random operations become repeatable. This reproducibility is essential for running experiments consistently and for debugging models and code. This line displays the version of TensorFlow currently in use. It provides a quick way to check which version of the library is installed. Knowing the exact version is important because different versions may behave differently. This helps with ensuring compatibility and makes debugging easier. We create a custom metric class called running mean absolute error that extends the TensorFlow Keras metric base class. This metric keeps a running total of the absolute errors and computes their average over time. By inheriting from the built-in metric system, it can use TensorFlow's tools for storing state and updating values during training. This allows us to track our model's performance in a way that is more tailored than using only the standard metrics. In the initialization method of this custom metric class, the parent class initializer is called first with the metric name and any extra settings. The method then creates one state variable to store the running total of absolute error, starting at 0, which will accumulate the absolute differences between predictions and true values. It also creates another state variable to count how many samples have been processed, again starting at 0. Later, the mean absolute error is computed by dividing the total absolute error by this sample count. The method first converts the true and predicted values to a consistent float type and checks that they have the correct column vector shape. It then computes the absolute error by taking the absolute difference between true and predicted values and sums this across the batch. The batch size is obtained by counting the number of true values, and this count is also converted to a float type. The method updates the running totals of absolute error and sample count using these batch values. Finally, it returns the current mean absolute error, computed as the total absolute error divided by the total number of samples so far. The result method computes the current value of the custom metric by taking the total absolute error and dividing it by the total number of samples. To make this calculation safe, it uses TensorFlow's divide no nan function, which prevents division by 0. If there are no samples, this function avoids an error and returns a safe default value instead. This ensures the metric is always well-defined, even when the sample count is 0. The reset states method clears the internal state of a custom metric between training epochs or evaluation runs. It sets the total absolute error back to 0 and also resets the total number of samples to 0. By doing this, each new evaluation or training cycle starts with a clean slate. As a result, the metric reflects only the performance on the current batch of data, not any previous calculations. We create a small synthetic dataset for a simple regression task by first choosing 128 samples. The input values are evenly spaced between -1 and 1 and stored as 32-bit floating point numbers. The target values are computed by taking each input, multiplying it by 2, and adding 0.3, then converting and reshaping them into a column vector. Finally, we reshape the input values into a matching column vector, so the inputs and targets have compatible shapes for regression. We define a simple keras model for linear regression by first creating an input layer that takes data with a single feature. We then add a dense layer with one unit and a linear activation, so it performs a basic linear transformation on that input. Finally, we build the model by connecting this input to the dense output layer. The result is a straightforward model that predicts one continuous value from one input feature. We create an instance of the custom metric class called running mean absolute error to measure how well the model is learning during training. This metric keeps a running average of the absolute differences between the model's predictions and the actual values. By setting it up, we can continuously track the model's prediction error as it trains. This monitoring step is important for understanding and evaluating the model's performance over time. The model is now being compiled, which prepares it for training. It uses stochastic gradient descent as the optimizer to reduce the loss. The chosen loss function is mean squared error, which is standard for regression problems. A custom running mean absolute error metric is also included to monitor performance during training. Together, this setup helps the model learn to minimize error while giving useful feedback on how well it is performing. The model is trained using the keras fit method, which takes the input and target data and runs for 3 training passes, called epochs. During training, it uses a batch size of 16, so it updates its weights after processing 16 samples at a time. The verbose setting is turned off, so no detailed training logs are printed, keeping the output minimal and focused. After training is finished, the code asks the custom metric object for its current value, which is the running mean absolute error. This result is computed by taking the total absolute error, dividing it by the total number of samples, and safely handling any case where the count might be 0. The value is then converted into a standard Python number for easier use with other Python operations. Finally, this running mean absolute error is printed to summarize the model's performance after training. We first inspect the total absolute error stored inside the custom metric to see how much absolute error has accumulated during training. Then we check the total number of samples that have been processed, which tells us how much data contributed to that error. Both values are converted to regular Python floating point numbers, so they are easier to read and interpret. To save the model along with its custom metric, we choose a file name and then call the model's save function with that name. This stores the model's architecture, its learned weights, and any custom components, including the custom metric configuration. Later, we can reload the model from this file, and all of these elements will be restored. This ensures the custom metric remains available and works correctly when the model is loaded again in the future. To load a previously saved keras model that uses a custom metric, we use the standard model loading function and point it to the saved file. Because the model includes a custom metric, we must also tell keras how to handle it during loading. We do this by passing a dictionary that maps the metric's name to its class definition. This lets keras correctly reconstruct and use the custom metric's behavior when the model is loaded. We evaluate the loaded model using its evaluation method, which takes the input data and labels to compute the loss and any defined metrics. We provide the data and corresponding labels and set a batch size of 16 to control how many samples are processed at once. The verbosity setting is turned off, so no output is printed during this process. This evaluation step updates the internal state of the custom metric, allowing us to measure how well the model performs after it has been loaded. The code takes the evaluation results from the loaded model and extracts the second value, which represents a custom metric. It converts this value to a floating point number so it can be used as a precise measurement. This number corresponds to the running mean absolute error after the model has been loaded and evaluated. Finally, the code prints this metric to the console to show how well the model is performing after loading. Before updating the metric, the code first checks that the input data and target data have the same shape. This confirms that every input value has a matching target value. Ensuring this one-to-one match is essential for computing the metric correctly. By verifying the shapes in advance, the code helps avoid errors during the metric update process. We take a small batch from our synthetic dataset by selecting the first few input samples and their target values. We then create an instance of a custom metric called running mean absolute error to manually evaluate this batch. By updating the metric with the true and predicted values, it computes and accumulates the absolute differences between them. Finally, we retrieve and print the metric's result as a standard Python float, which gives the mean absolute error for this small batch. This script shows how to create and use a custom metric in TensorFlow to track the running mean absolute error during training. It defines a metric class that keeps a running total of absolute errors and the number of samples, then applies it while training a simple linear regression model on synthetic data. After training, it reports the final running mean absolute error and the internal state of the metric, then saves and reloads the model to verify that the custom metric is correctly restored. The script also manually updates the metric on a small batch to illustrate how its running values change, demonstrating how to implement, apply, and persist custom metrics in a machine learning workflow. Resetting metric state. Resetting custom metrics is essential to keep evaluation results clear and reliable across training, validation, and testing. Metrics often accumulate information over many batches, so if they are not reset, they can mix data from different epochs or datasets. This mixing can make performance measures, such as accuracy, look better or worse than they really are, for example, when evaluating a medical model on new data. By resetting metrics at the appropriate times, each reported value reflects only the intended data, preserving the integrity of your model evaluations. When using custom metrics in complex workflows, you must reset their state between different evaluation phases to keep results accurate. For example, a fraud detection metric that tracks false alarms and correct detections should be cleared at the end of each epoch before processing new data. The same reset is needed when moving from training to validation or testing, so each phase is evaluated on fresh data. If you do not reset the metrics, they can mix information from different phases and produce misleading results that undermine fair comparison and decision-making. Resetting the state of custom metrics is important when saving and loading models, especially in production or shared environments. You want to keep how the metric is defined, but clear out any temporary data from previous runs. For instance, when a recommendation model is reused to evaluate new user data, the metric should start from a clean slate to give accurate, up-to-date measurements. If old data is kept, the metrics may react slowly to changes and hide real performance problems or improvements. By reliably resetting metrics at key points, you keep past and current evaluations clearly separated and support better monitoring and decision-making. Python code, resetting metric state. This script demonstrates how to reset the state of a custom metric during training. It uses a very small model and synthetic data so you can clearly see how the metric behaves. The main goal is to highlight how the metric changes across different phases and how resetting its state affects the results. The commented line recommends installing TensorFlow version 2.20.0 to match the code that follows. Using this specific version helps avoid problems caused by changes in features or syntax between different releases. It serves as a reminder to set up the software environment correctly before running the script so everything works as intended. We begin by importing a few key libraries needed for our work. The operating system library lets us interact with the file system and environment settings. The random library allows us to generate random numbers, which is useful for tasks like shuffling data. We then import NumPy for efficient numerical computations with arrays. Finally, we bring in TensorFlow, which we will use to build, train, and evaluate our neural network model. We set a seed value of 42 so that our results are the same every time the code runs. This seed is applied to Python's random module, to NumPy's random number generator, and to TensorFlow's random operations. Using the same seed across these libraries controls all sources of randomness in the script. This deterministic setup is essential for reproducibility because it lets us repeat experiments and get identical results on each run. We briefly display the TensorFlow version in use to verify that the environment is set up correctly. This confirmation helps ensure that the code is running with the expected version. It is especially important when relying on specific TensorFlow features or when tracking down version-related bugs. By checking the version, we can avoid compatibility issues with the rest of the code. We defined a custom metric class called simple accuracy that extends TensorFlow's metric base class. In its initialization, we give the metric the name simple accuracy and create two state variables, one to count the total number of examples and another to count how many of those examples are correct. These variables are created using TensorFlow's method for adding weights, so they can be updated during training. Both are stored as floating point values to maintain precision in the accuracy calculation. This method updates the metric by first flattening the true labels into a one-dimensional tensor and converting them to integers. It then derives the predicted labels by taking the index of the largest value in each prediction and also converts these to integers. The method compares true and predicted labels to find which predictions are correct and turns these matches into a float tensor. It computes how many examples are in the batch, adds this to the running total of examples, and adds the number of correct matches to the running total of correct predictions. In this way, the metric's internal state is updated with the new batch of data. This method computes a custom metric by taking the number of correct examples and dividing it by the total number of examples. It relies on a TensorFlow function that performs division while safely handling cases where the total count is 0. This prevents division by zero errors and ensures the metric is always computed in a stable way. The reset state method clears the internal counters of a custom metric so you can start measurement from scratch. It sets the total number of examples back to 0 and also resets the number of correct examples to 0. This removes any influence from previous runs and is especially important when switching between different evaluation phases, such as moving from training to validation. The getConfiguration method is used to retrieve the settings of a custom metric. It first calls the parent class's getConfiguration method to include all default options. It then returns this combined information as a dictionary. This design allows the custom metric to be saved and later restored with its configuration preserved, supporting proper model serialization and deserialization. We begin by defining the basic setup for our synthetic classification task. The model will sort inputs into 3 classes, and each data point will have 4 features or attributes. We create 64 samples for training the model and 32 separate samples for validation. This structure gives us a clear and organized way to generate data, train the model, and then evaluate how well it performs. We create synthetic training data by drawing random feature values from a normal distribution, forming a two-dimensional array with the desired number of samples and features. Then, we generate random integer labels for these samples, choosing from a fixed number of classes to simulate a classification task with discrete outputs. We repeat this process for the validation set, producing random features and labels of the appropriate size. This synthetic setup lets us train and validate a model, so we can study how the evaluation metrics behave in a controlled environment. Before building the model, the code checks that the training data has the expected number of features, making sure the input shape matches what the model requires. It performs the same check on the validation data to confirm it is also correctly structured. These assertions help detect any mismatch in feature dimensions early, so errors do not appear later during training or evaluation. We build a simple neural network in Keras by first defining an input layer with a number of features set by a variable for the feature count. We then add a dense layer with 8 units and a ReLU activation to introduce nonlinearity and transform the input data. After that, we add another dense layer whose number of units matches the number of classes and use a softmax activation to produce class probabilities. Finally, we connect the input and output layers into a complete Keras model that is ready to be trained for classification. We create an instance of the custom metric class called Simple Accuracy, named Train Simple Accuracy, to track how well the model performs during training. This metric measures accuracy by counting how many predictions are correct and dividing by the total number of predictions. Using this custom metric lets us see how closely the model's predictions match the true labels. It is an important part of evaluating the model's performance as it learns from the training data. The model is now being compiled, which prepares it for training. It uses the Atom optimizer, which is well suited for training large and complex models efficiently. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when the labels are integers. A simple accuracy metric is also included, so we can track how well the model is performing as it learns from the data. Together, this setup helps ensure the model is optimized correctly and its accuracy is monitored during training. The model is trained using a fit function that takes the training data and their labels as input. It runs for 2 epochs, meaning it goes through the entire dataset twice. The batch size is set to 16, so the data is processed in groups of 16 samples at a time. The verbose setting is turned off to suppress training logs and keep the console output minimal. After training the model, we evaluate its performance by calling the result method on our custom training metric to compute the current accuracy. We then convert this value to a standard floating point number using a numerical library. Finally, we print the metric, rounded to 4 decimal places, to clearly see how well the model performed during training. We reset the custom metric so it starts from a clean state for the next evaluation phase. This is done by calling its reset function on the training metric object. After resetting, we check and print its value, which should be 0, to confirm the reset worked. This prevents any leftover values from training from affecting validation, ensuring the evaluation results are accurate. To evaluate the model on the validation data, we call its evaluation routine with the validation features and labels and use a fresh instance of the metric. We set the batch size to 16 so the data is processed in small groups, and we turn off verbose output to avoid printing progress during evaluation. The evaluation is configured to return the results as a dictionary, which makes it easy to look up specific metric values afterward. We report the model's validation performance by printing the accuracy score computed on the validation dataset. This score is taken from the evaluation results dictionary using the entry for training simple accuracy. We then round this value to 4 decimal places to make it easier to read and compare. This step gives a clear measure of how well the trained model performs on unseen data. The code saves the trained model to a file so it can be used later. It uses TensorFlow's save method to store the model's architecture and learned weights at a specified location. The optimizer is intentionally not saved, so its internal state is not kept. This setup is useful when you only plan to use the model for making predictions rather than continuing training. To reuse a previously trained model in TensorFlow, you load it by giving the path to the saved model file. If the model was built with a custom metric, you must also provide a mapping that tells TensorFlow how to find that custom class. In this case, you specify that the simple accuracy class is the custom metric. This allows TensorFlow to correctly recognize and apply the custom metric when the model is loaded again. We evaluate the loaded model on validation data to confirm that its metric state is fresh and not influenced by earlier evaluations. The validation set includes both input features and their corresponding labels. We use a batch size of 16 to control how many samples are processed at a time, and set verbosity to 0 to avoid detailed logging in the console. The evaluation results are returned as a dictionary so we can easily access specific metric values. We report the validation metric obtained from evaluating the reloaded model. To do this, we access the stored metric value from the evaluation results and round it to 4 decimal places for clarity. Printing this rounded value gives a clear summary of how well the reloaded model performs on the validation data. This script shows how to reset the state of a custom metric in TensorFlow while training and evaluating a simple classification model. It defines a custom accuracy metric that tracks the ratio of correct predictions to total predictions, then trains a small neural network on synthetic 3-class data. After training, it prints the metric value, manually resets the metric state, and prints the value again to confirm the reset. The model is then evaluated on validation data, saved, and reloaded to verify that the custom metric is properly restored. Finally, the reloaded model is evaluated again, demonstrating that the metric state starts fresh and remains accurate across training, saving, and loading phases. In this lecture, you learned to implement custom keras layers by subclassing tf.keras.layers.Layer with build and call methods. Define custom loss and metric functions or classes compatible with keras training workflows. And integrate custom components into models and verify they save and load correctly. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.